Good morning, good afternoon, and good evening to viewers around the world, and welcome to our fourth Global Reaxys User Day. My name is Eric Siemens. I lead the Life Sciences Solutions sales team for EMEA at Elsevier, and I have the honor of being your host for today. And it's great to see you all, our chemistry community, come together here online. Whether you're a synthetic chemist, a data scientist, or just curious about how digital tools are reshaping discovery, today's sessions are designed to spark ideas and conversations, and it's all about the future of chemistry. This event is recorded live, and we have some great speakers lined up for you. We'll hear from leading voices in the field who are not only pushing boundaries in the lab, but also rethinking how we work with data, how we collaborate, and how we innovate. Now, before we start, let me go over a few housekeeping topics. First, yes, we will make recordings available after the sessions, so you can re-watch or view presentations that you might have missed. There is a chat function that you can open at the bottom right of the screen. The Q&A menu will then show, and we encourage everyone to ask any questions you might have during the sessions. You can easily click at the top right to go from chat to Q&A to polls, and in the handout section, you can download handouts. There's also, I'm going back one slide, there's also a closed caption option for subtitles. So for this, you click the CC button and then you select your preferred language to display online. So please do enter your questions in the Q&A tab so that we can see and answer all of them. And if we can't answer a question live, we will make sure that we answer it after the event. And so finally, please also share your feedback with us. We'd like to learn and make this event even better for next year. So let's start with the first two speakers of today. It is my pleasure to introduce Professor Philippe Schwaller and Dr. Markus Fischer. Professor Schwaller is currently a Tenure Track Assistant Professor at the Institute of Chemical Sciences and Engineering at EPFL in Lausanne, where he leads the Laboratory of Artificial Chemical Intelligence. His group is at the forefront of AI-accelerated molecular discovery and synthesis, and he's truly pushing the boundaries of what is possible in chemistry with AI. Philippe obtained his bachelor's and master's degrees from EPFL, then went on to work at IBM Research, during which time he also completed an MPhil at the University of Cambridge, and he then earned his PhD in chemistry and molecular sciences as part of the Raymond Group at the University of Bern. Beyond his research at EPFL, Professor Schwaller is a core principal investigator of NCCR Catalysis, a Swiss Center for Sustainable Chemistry Research, Education and Innovation, and he also co-leads the science pillar in the Swiss AI initiative, reflecting his commitment to both scientific advancement and interdisciplinary collaboration. Dr. Markus Fischer currently serves as Senior Product Manager at Elsevier, where he leads API and technical integration solutions for Reaxys. Markus holds a PhD in chemistry from the University of Stuttgart in Germany, where he specialized in protein informatics. Following his doctoral studies, he held a postdoctoral position at Columbia University's Honig Lab, where he contributed to the Structured Genomics Initiative. Then, moving into product management at Schrödinger, Markus contributed to the development of the Live Design platform and the protein ligand database, supporting advancements in drug discovery. He joined Elsevier in 2016. Today, Professor Schwaller will share insights from his work in his talk, Teaching Language Models to Speak Chemistry. Please join me in welcoming Professor Philippe Schwaller to the stage. You're on mute, Philippe.
Yes, let me unmute and share my screen here. I want to share. Now it's sharing the entire screen. Good. Can you see my screen now? All good?
Almost. It's still loading.
Is it good now?
It's not yet showing.
I'm on my side. It's like I'm sharing the screen. Can you see it?
I see some responses in the chat. So on my screen, I can't see it. Let me check with the colleague. All right, your slides are showing. Please go ahead.
Okay, good. Perfect. Thanks so much for the super nice introduction. It's a pleasure to be here today and talk.
Audience view.
Yeah.
Can I make it bigger, the audience view?
Can you see it now? Okay. I will just go ahead and let me know if there's some technical issues. But in chemistry, you probably all know that we have a nearly endless space to explore. If we take drug-like molecules as an example, then the estimated number is 10 to the power of 60. My lab at EPFL is like kind of thinking about how can machine learning help us to accelerate the chemical design cycle from what molecule we want to make, mostly with applications in drug discovery and catalysis, or to how to make them, because this is kind of not straightforward, so we can get closer to experimental validation. And today I will be mostly talking about language models. And what I mean by language models is you have some kind of neural network and it's trying to predict the most likely word in natural language, or for example, the next atom in chemistry. And if we took an example from natural language, then and it was trained on yesterday's data, it would be maybe outputting something like Philippe Schwaller and prepare slides for the global Reaxys user day. In chemistry, we have kind of to find a text-based molecular representation to be able to apply the same techniques. And luckily, back in the 80s, even this mice representation was developed. And here you have an example how a molecule can be written as a string. And you see the C and C and so on, and goes through. You have the branching here with the brackets and the ring opening and closing with the numbers. And really what this allows us is to borrow methods that were developed for human languages and apply them to chemistry. If, for example, we would like to teach a language model to generate molecules of interest, we would take a big database of molecules, could also be the ones from Reaxys, encoded as smiles, and then we would just train that model to generate molecules atom by atom. And but the problem there is that they're very good at learning the distribution of the initial database. But what we are mostly interested in often is to kind of have molecules with a particular property profile. So to do that, we take a model that has kind of learned to generate molecules correctly. And then we enter we sample that model, we calculate some scores that tell us how close the molecules are to the desired property profile. And based on those scores, we update the model and sample a new batch. And we kind of, using reinforcement learning, bias the model towards a space with interesting properties. But scoring and labeling is often very expensive. So what my lab is working on is to develop sample-efficient techniques. And we have we introduced augmented memory, which was very much based on reinvent, and then our own framework called Saturn that decoupled it a little bit from reinvent and used another language model inside. What we can do now with Saturn, for example, is this is just an example in organocatalyst discovery. We could take, for example, the Morita-Baylis-Hillman reaction, which was kind of also where other generative models have been developed by the Jensen group. Then we can take a physics-based oracle and pre-train a language model on tertiary means from zinc, for example, and then enter this generation scoring and updating loop. And using that approach, we can identify new bifunctional catalysts that could potentially catalyze this Morita-Baylis-Hillman reaction. What is fascinating for me is that those language models can act as kind of idea generators, and the top candidates are now being synthesized by an experimental group. And what is always surprising for me is that although we generate in 2D as mice, those models are able to learn 3D functionality. And here on that slide, I just have one example where you see how the model learned to generate a bifunctional organocatalyst with the amine here that is imported for the MBH reaction, rigidified linker that has the exact length that is required to place the hydrogen bond donor on the other side and stabilize the transition state. What is always kind of a key issue is synthesizability. And this is also where we are kind of trying to push, and what could really be augmented by the Reaxys tools. And this is just to show you a use case where we kind of not only want a desired property profile, but also a synthesis to those potential molecules. And imagine you have different constraints. You want to buy from a specific vendor. You kind of also want to use somewhere in the synthesis some waste materials that are regional. And then you would like to kind of not only enforce that, but specific reaction types. You want to ensure that you can do those, synthesize those molecules. So you want to use mi bond formations and Suzuki couplings because those are your favorite reactions. So you kind of want all those constraints plus docking scores that are low and high QAD. And in a recent preprint with Jeff and Victor from my group, we actually managed to generate interesting molecules that fulfill all those types of constraints. And yeah, but we can use language models also differently. In the first part here, I showed you smiles-based language models. Now we will move more to general purpose large language models, as you know, for example, from ChatGPT. If you have just a simple language model, you have a user query, and based on this context, it will just generate a confident answer word by word. But often in chemistry, we push them outside of what they have seen in the training. So they will just start hallucinating. What we can do to overcome that is to give them the ability to take actions, and then they can kind of access external tools, which could be database queries such as Reaxys API, web search, other chemistry tools, whatever you want. And by giving them the ability to access this additional information and take that into the context, it can reduce hallucinations, and better tools lead to better task solving. We investigated this idea in our ChemCrow work, where we gave a language model agent access to different chemistry tools, from like molecular tools to general tools, reaction tools, and also some safety tools, and then really like gave the model the task to like think about the query provided, select an action, generate the input to that action tool, and then take the now more precise observation to continue this loop until it gets to a final answer. And just one example that we had in this work was kind of planned and execute the synthesis of an insect repellent. So it first had to find out what is an insect repellent, quite the literature, found different molecule names, selected DEET, but DEET didn't provide any structural information. So it had to select another tool to convert DEET to the actual structure. Given that, it could use the reaction planner to get back not only a synthesis plan, but also a recipe to actually perform that reaction. And because we connected it to a robotic platform, it could execute that reaction on the Reaxys, and after 2 hours, we had DEET confirmed. What is always challenging with those larger workflows and large language models is to evaluate them. And together with Kevin Jablonka, we worked on ChemBench, where we digitalized more than 2,000 multiple choice questions from university exams and chemistry Olympiads and so on. And what is kind of surprising is that some of the common like closed source models are now getting much better than the average human, and you can try to like compete yourself against those language models on ChemBench if you would like to do that. But there's always the question, if we are measuring the correct thing with multiple choice question, and we wanted to push forwards to more useful tasks. And what we quickly realized with my team at EPFL is that language models by themselves, those general purpose language models, were not amazingly great at generating molecules or reactions. They made a lot of mistakes, but they were very good at analyzing them if you gave them the SMICE, for example, as an input. And we made use of that to basically combine natural language and expert queries with traditional retrosynthesis algorithms. And what you can do is you can align those different solutions that you get from a retrosynthesis tool with an actual expert query. This is here is just kind of one example for this kinase inhibitor by Merck, and there you could, for example, query for break pyrimidine in the early stage, but get all other rings from commercially available molecules, and the language model is able to like analyze every single step and then give an overall assessment of how well a route like matches with an expert query. And this gives you a totally new way of going through the output of computer-assisted synthesis planning tools. And this is best shown in a video where you can actually like kind of this is just a small interface that we built, but it can basically have anything in the back, for example. So you could take Reaxys a retrosynthesis API. You can put a steering prompt. It kind of scores now the routes differently and looks exactly whether it matches the actual steering prompt or not. And here we find a route that matches the late imidazole ring formation. And here you see how the language model analyzed all the different reactions and gives an overall assessment. This gives you just a new way how you can navigate those hundreds of outputs that you can get from retrosynthesis planning tools. But now that you kind of have a synthesis route, you still need to kind of optimize the single steps. And a few years back, we had this wonderful paper by Abigail Doyle on like Bayesian optimization for chemical reactions. This works super nicely, but every time we kind of enter a discussion with a group like that has a different reaction that they want to optimize, the question becomes like, what descriptors should we use? Should we use similar to this original work, like DFT descriptors? If so, which ones, and so on. So what Bojana in my group like worked on is like working on more holistic representations using large language models. And 1.5 years ago, we used like fixed features, like just because like what LLMs are really good at is like to convert whatever text you have, and you can describe any molecule and or synthesis procedure as text into a vector which can be used as a representation of your reaction. And back then we were not matching the best chemical features that we had available, but more recently in this preprint we kind of introduced an approach to jointly train like the large language model during the optimization with the surrogate model. And what we can see in that work is that large language models are amazing feature extractors, and we can quickly adapt them with a few tens of data points to the actual reaction of interest. And you can see how the representation space quickly adapts to something that is much easier to optimize. We tested that approach on procedures, on smiles, on different pre-trainings, chemistry-based, natural language-based, on different architectures. So in language models, you have decoder, and encoder architectures. It works nearly the same for all of them. And we also benchmarked it with the same set of hyperparameters on 19 different chemistry-related tasks. So it's kind of a super nice approach that like kind of overcomes the typical like first few months of like discussing about what is now the best representation to use for a given new reaction. And yeah, today I've walked you through like small language models trained on smiles for sample efficient molecular generation, then large language models more for chemical research with access to different tools, and in the end also how you can use them to like learn even in the low data regime that we typically face in chemistry. So I'm super excited about all those directions that we can take with language models in chemistry. And with this, please let me thank the team and also Reaxys for giving me access to their data, to the API and everything, and inviting me to speak to you today. I will now hand over to Markus, and thank you very much for your attention.
Yeah, thank you so much, Philippe, for this inspiring presentation, actually. So now what I would like to present you is actually how we utilize now such capabilities through AIs in Reaxys. And let me actually share my screen. So now just need to see this is
Your screen is being, or your presentation is being shared, Markus. So if you like, I can also press the button.
I would like to give a live demo, so therefore I also would like to, I'm just trying to figure out which screen is actually, let me here.
For me, it was on top, the
Here
entire screen sharing.
Yeah, thank you, Philippe, exactly. So I hope now my screen is loading. It looks like you should see now actually my presentation. So, and as I mentioned, so what I would like to guide you through is actually how we now within Reaxys utilize AI to give you really the best user experience as possible. And for that, I would like to run you through actually our tool, which is the predictive retrosynthesis tool, which we have developed in close collaboration with ICTOS. So now it is not a surprise that synthesis planning obviously is one of the most important use cases within Reaxys, and therefore it was also a natural extension to combine actually our data set with these AI machine learning capabilities to come up actually with a functionality which allows now to assist synthesis planning using predictive retrosynthesis within Reaxys itself. And for that, actually, we collaborated closely with partners. One was ICTOS, which I will focus on today, but we also have a collaboration with Pending AI. If you would like to learn more about the Pending AI module, feel free to join tomorrow my colleague Timur, who will then also go into more details around that module itself. So before I go into the live demo, I want to give you just a few details around the tool itself. So the predictor we developed with ICTOS is actually a so-called template-based approach, meaning it derives from the test data set rules which are representing chemical transformations. And actually, to do so, the ICTOS team was utilizing 16 million of the Reaxys data to actually derive then an impressive number of 450,000 rules, which are then utilized actually to predict for your target molecule the individual steps within the synthesis route. I think that's also a great testament for how diverse and comprehensive the Reaxys dataset is actually covering the chemical space with regards to reactions. Now, in combination with the neural network, plus a really very efficient and quick Monte Carlo tree sampling algorithm, the ICTOS predictor now really is capable of giving you really very scientific, robust routes for your drug-like small molecules. It also offers customization options where proprietary data can be included in the modeling process itself. And with plenty of configurations options, I will show you just in a minute in the live demo, it really helps you to quickly get results where you can actually really tune the entire prediction according to your needs and strategy you would like to apply. Now, with that said, let me just quickly jump into the demo. And for that, I just want to start actually here with the retrosynthesis view. So the ICTOS tool is really nicely integrated within Reaxys itself. So you can quickly get there by just opening up the retrosynthesis tab. And then what you will see is actually your project page. So here you will see all the different kind of target molecules you were previously processing and asking to predict routes for. Now, to actually start a prediction, you simply can go to the drawing tool by clicking here or up here. And what that will do is actually it will open up the sketcher where you have actually the possibility to select between Marvin.js or ChemDraw. Now, to actually input your target molecule, you could utilize obviously the different kind of drawing tools within the sketcher, or you could utilize the insert structure function where you could look up existing molecules by chemical name, the Cas number, or what I would like just to do, you could also just enter smiles, for example, to then insert the molecule directly into the sketcher. So this is now the molecule we were selecting for this little demo. And so once you have drawn actually a molecule, then you will see here on the right side that there is, as mentioned before, really a lot of information and parameters you can choose from to actually really fine-tune how the prediction should run. So let me just quickly guide you through some of those parameters. So one would be that you have actually control over the number of steps you would like to include. So this obviously will allow you to restrict the length of the path the ICTOS tool should actually prepare for you. And here you can select between 2 or 15 steps. There are also options like that you can ask to ignore stereochemistry. So if stereocentric atoms are present, you can avoid using them. Another option, obviously, is then here also the possibility that you can exclude regional selective reactions. That is really important also if you want to avoid that reaction templates are utilized, which could cause then in the experiment regional selective issues. And very important part also of the algorithm is actually the starting material libraries to utilize for the predictions. So here you have two options. You can actually select the subset of our commercial substances which are deliverable within 10 days. Or you could also select the entire commercial substance data set as building blocks, which is around 150 million of compounds. So beside those options, you also have here the possibility to define an upper limit for the max price per gram. And now in combination of all those options, you can really now tune and configure the tool according to your needs. So which strategy you would like to run, but also in which stage you currently are with your research, and potentially make then the routes more realistic in terms of availability of compounds, or just to get ideas around what in general is possible. Now, besides those options, there's also the possibility to set the processing time. So where you have the standard, which is 10 minutes, but also if your molecule is more challenging, you can extend that to a longer runtime. And all the information for the options is also nicely described here in the different kind of pop-ups, where you can just double check what exactly the settings are doing. Now, besides those options, which are more or less controlling the overall process of the prediction, there are also options which allow you actually to configure what chemistry should be utilized for the predictions. So, and for that, there are actually two options I want to show you. So one is the nice feature that you can actually include intermediates. So up to 10 intermediates you can specify which should be included as a substructure within the overall route and the individual steps, or up to 10 intermediates which should be actually excluded. So that is really helpful, for example, if you would like to avoid certain kind of toxic compounds by excluding them. But on the other hand, the inclusion of intermediates also could be very helpful if you would like to see if your route can be routed through actually a hub molecule, which you prefer to have overall in your synthesis plants. So that is one option actually to control the chemistry. On the other hand, there's also a nice feature that you can actually utilize labels to protect or to break certain bonds within the molecule. So for example, you could request that this bond here should be broken, or you can also define that, on the other hand, this should be actually protected. So those functionalities really help you also now to guide the system through certain chemistry you would like to have be included in the predictions. Now, once you have chosen your settings, you simply submit the synthesis plan. And obviously there are a lot of options you can pick from. So if you get just started with the tool, actually, you can also start with the default settings, which we have actually tuned for the most robust predictions for general use cases. So, and in doing so, you just simply click then synthesize, and that will now move you over into the project view we have seen before. But now here you can identify that actually the molecule has been now submitted and the prediction is ongoing. So what you also have here on the project page is actually that you can see the parameters you have chosen for the prediction. So that is also quite helpful if you come back later and to identify what parameters have been used, also for the reporting to colleagues. But also if you have a bunch of different kind of settings you would like to apply to one given molecule, you quickly can look up which of the different kind of projects was utilizing specific parameters. Now, since the prediction will take up to 10 minutes, let me actually quickly open up a already completed run for the molecule, just to give you an idea how you can now actually inspect the results. So if you open up a project, the first thing you will actually see is now here the overview of all the routes which have been identified by the predictive retrosynthesis tool. And there is a lot of information which already helps you to actually browse through and identify which of those routes are of most interest to you and seem to be most feasible for further in detail inspection. So one part is that you will see here, obviously, all the starting materials which have been identified within the predicted route. For each of the starting materials, you also have an overview of actually the commercial availability. So you can look up here the shipping time, but also the best price. And additionally, also the package size for the individual starting materials. If you're interested in, there's also the possibility to look up more details around the molecule, which are present in Reaxys. And besides the starting materials, then you also see actually here the number of steps within the route itself. And in combination with the topology, which is shown here, that also helps you to assess actually the complexity of the overall route, and if this is something you would like to investigate further. Besides that, you also have here illustrated the first disconnect, which is highlighted here in green. So this is actually then the last modification, which is done for reaching your target molecule. Now, there's also a score which represents the overall confidence of the system that it's actually a feasible route in terms of the prediction. And if you're interested in understanding what the details around the score are, there's also this nice description, which gives you all the information to assess actually the routes based on those scores. Now
we are almost at times, and there are some really interesting questions.
All right, let me then really quickly go one more minute, because then I will just show you actually how the results look. So this is one example. So obviously now you see the entire route. The interesting part is that for each of the individual steps, you will be able here to see then actually more details around the experiments, meaning all the reactions which have been actually identified as similar within Reaxys. And here you will then actually see the different kind of conditions for the reactions. And that helps you then obviously also a lot to assess how relevant the step itself will be. So unfortunately, the loading is okay. Here's another example. So this is what I wanted to show you. So for each of the steps, you will actually identify the interesting examples. So besides that, there are ways to modify, export, and copy over the individual routes into, for example, ChemDraw for then reporting. But let me then stop here. I hope that was actually helpful as a quick overview how we actually utilize with ICTOS AI and our reaction data set within Reaxys. So, and then with that,
so much, Markus.
Let me
and
stop
thank you,
sharing.
Philippe, also for a really interesting talk. We are, I think, just getting started with the powers of predictive technologies. I see some questions, and unfortunately, we don't have the time to go to a lot of discussion around it. But I see some questions on how can we move from relying heavily on patterns of what we know to more reasoning type of capabilities in these predictive models, which I think is a really interesting topic that you must be working on, Philippe, with your group. And to that end, Apple researchers published a paper just a week ago around the illusion of thinking and sort of understanding the strengths and limitations of reasoning models via the lens of problem complexity. That might be a really interesting topic for a next talk. Actually.
Yeah, definitely. Yeah, no, but like kind of, yeah, I think like this. The key here is that if you have access, if you give language models access to huge databases like the one from Reaxys, I think they can extract the patterns from that, and they would never be feasible for a human to go through all that information, even in a lifetime, I would say. So it kind of maybe like. If you have an expert chemist that knows like a small field of chemistry super well, the language models will not match that. But like if you have more newcomer or like kind of someone that wants to perform reactions slightly outside the domain of expertise, then a language model is perfect to kind of learn from all the data that is available and point to like the important reactions that could potentially be performed, and maybe also like recover one reaction that was not frequently used and kind of display that as well. And I think like Markus showed the perfect example, like with the output from Ictos, where you have tons of possibilities, and if you would bridge that with a natural language interface, you could actually chat to those synthesis routes and like reorder them according to what you kind of have an idea about, but that didn't come out as the top one, and it will.
The future of chemistry is really exciting, also with the help of these technologies. Thank you both so much for these interesting talks. For the audience, thank you for being here. There's a link to a short 5-question survey in the chat. Please do share your feedback with us by clicking it. This session will end shortly, and then you can just wait and you'll be moved into the next session automatically. Thanks again, Markus, Philippe, and have a wonderful day.
Thank you
very much.
Bye-bye.